Alright, so welcome back again, and this is the Chipmaster here. Right, so today I'm going to do another repair video on a laptop, an old school HP I have here. It's already disassembled by the tech, and they said that it's not turning on. It says no power. Right, it's written no power. Right, so it's already disassembled, so I will just head over to the overhead. So got it as is. This is the way I got it. Alright, let me just get my adapter. I don't want to pull this one because the hinges are normally easy to break. I don't want to pull it. Alright, so the greatest thing is that the laptop was already disassembled. Alright, so let me plug in the power and see what we get. Alright, this is the first time I'm gonna touch this thing. I get 120 milliamps, so that's a short. Could it be that this is a AMD CPU, which is the Kabini, I believe. The AMD's APU, which is the Kabini's. Alright, this is the Kabini. Alright, let's check some visual inspection again. Let me see if I check this side for any corrosion or liquid spill or any explosion. This is in the RTC section. All good. Alright, should be for the RAM power supply here. All good. This coil should be for VDD-CR 0.95 volts here. Alright, this is the VCC. This is the core section. This is for the north bridge. One for the north bridge, and this is the CPU core supply. Right, VDD-CR SOC_CPU, which is the signal standard name for this APU as well. Right, this is the APU, which is the Kabini. Alright, in the charging section here, all good. There's no burn, any form of liquid intake. Alright, let's check the standby area. Alright, this is 3 volts and 5 volts, I believe. Alright, this is the standby chip. There's no fault there, as in no liquid spill. It might have a fault, but I don't. This is the audio section. Alright, this is the embedded controller here. Maybe it is the culprit, I don't know. This is the CPU. This is the power management chip for the Kabini CPU power supply APU. And this is our charging IC here. I don't see any issue there. Let's look under the Kabini. Alright, I don't see any issue there. Let me just zoom in some more. Alright, I don't see any issue there. Alright, down here. It should be for the RAM power supply. Not seeing anything obvious. Alright, so I'm going to clean off this dust. It's a bit dusty. Alright, so here we go again. Alright, so I'm gonna, based off my experience, I'm gonna feel the standby chip if it's getting hot. Yes, it's hot. It's hot. Yes, it's yes, it's hot. That one burned my finger there. Yes, so I don't have to put this under the, well, the thermal camera. So this is hot. 99% of the times when these chips get hot, it's not the problem. Many techs always go ahead and change it. It's not the fault. It's actually a short somewhere, right? So most likely the linear section inside of the chip is shorted, so the voltage cannot be released, right? So the tension is on that line, right? So the chip will get hot because it needs to release the circuit, right? And to the current that is built up inside causing it to get hot because it needs to release the voltages and the current, right? This is a milliamps of current because a linear voltage only provides roughly 300 milliamps of current, right? While a PWM circuit can put up for the 5 volt and 3 volt standby section can output up to 7 ampere of current, right? So normally when there's a short, when this chip gets hot on the PWM standby area, normally the RTC section is shorted, which is most likely a dead short cap, or it can be a dead CPU that is shorted in the RTC section. And secondly is the embedded controller that is shorted, right? So the embedded controller normally wants 3.3 volts linear voltage with about 100 milliamps of current in order for it to produce the standby voltage for the embedded controller, right? So most of the time people will tend to replace the chip, and it still gets hot and they get confused there. So when a chip is getting hot, most of the time it's not a faulty chip, it's a short on the rear stage, right? So I'm going to head over to the embedded controller section under the microscope rather. Right, so first let me check the linear pins around it. This is let me head for the schematic just for clarification and for demonstration. I will head over to the schematic. Okay, so for this model, it is the LA C781. It's LA, turn on the caps off. LA, that's just a hyphen, right? C781. And I don't have a schematic here. Interesting. So it's just some BIOS files. Let me try there. Just LA hyphen C781. And there's no schematic for this model, so I'll go for something closer. I think it's a LAD781. Let me confirm. Well, I was unable to find a schematic, so I'll just have to use my experience, right? So at times when you're repairing these stuff, after a couple of years of doing this, then you have a rich experience on repairing these boards. So I'll now use my brain. So let's do this, shall we? Alright, so I'm going over to the standby section again, and I'm going to check around the chips here. Alright, this chip 8A, it says 8A2H. As you can see, it's 8A2H, and that's a rich tech chip, right? And I'll see if I can find a data sheet for this one, right? It should be a RT82. It's not a 49. RT82. Let's see if I can find a data sheet since we don't have a schematic. So I'm going to head over and see if I can find a data sheet, and we'll be right back. Okay, so I found the data sheet. It's a RT8243. So I was close because I know that RT8249 normally starts with 2C. So this starts with 8A. So once it's at 8A, you know that it's an RT8243AZ, right? If it's an 0B, it's an RT8243CZ, right? And if it's 7A, it's an RT8243BZ, right? So we have A, B, and C, as you can see. All right, so it's a A, B, and C revision, and as you can see, it's a dual step down switch mode power supply, right? Controller which generates logic supply voltage for battery powered systems, right? Including 2 pulse width modulation PWM controllers, which is adjustable from 2 volts to 5.5 volts, and an LDO 5 volts. All right, and it has 5 volts and 3.3 volts linear fixed. So this is the part that I'm interested in, which is the linear voltages, right? So 3.3 volt linear and 5 volt linear. Normally, the 3.3 volt linear section is normally shorted, as I said before. If it is shorted, normally the CPU RT section is shorted, right? Which is most likely a dead PCH or a dead CPU, or the embedded controller, which we call the EC, or the IO controller. What is called, I normally call the embedded controller because it has a firmware inside, right? Or it reads a program in order to configure the GPIO pins. And so I'm going to go down to the pinout definition here, as you can see. So I'm 8A. So I am using the RT8243A because mine starts with an 8A, as you can see. All right, let me get over back to the schematic. Oh, sorry, to the microscope. Let me show you again. So as you can see, it's 8A. All right, so as you know, it's an RT8243A because it begins with the 8A. Right, so that is the product code number there. Right, so let me get over back to the all right, good. So I'm using RT8243A because it begins with an 8A. All right, so this is A, B, and C, which is the same here. So A is different from B and C. So I need to check LDO 3.3 volts. All right. So LDO 3.3 volts is pin number 15. All right, and LDO 5 volts is pin number 14. So I need to check pin number 15 if it is shorted. All right, so I'll have to inject some voltage on this line to see if the APU is broken or the embedded controller is broken. But for the Intel platform, most of the time, if it depends. The Intel platform normally have a shorted RTC section. I rarely find an AMD APU has an RTC section that is shorted. Right, so most of the time for the Intel, sometimes it's the embedded controller and sometimes it's the PCH or the CPU. So I will check pin number 15. Pin number 15 here, as you can see. So this is pin number 1 mark. Right, so we have 5, 10, 15. And this is cap here. As you can see, I'm getting a dead short to ground here, as you can see. Let me. Alright. So here's the linear capacitor for pin number 15. So it's 5, 10, 15. As you can see, I'm getting a short on both sides of this cap here. See, 0, 0, 0 on this side, 0, 0, 0. So that is why it's hot. That is why the chip is getting hot, because it says it's in a short there. Most people will go ahead and replace this chip, but it's not. The chip is the problem. I can guarantee you that. Okay. Here is the test, the jumper point PJ1. So I measure here as well. It is dead short. So I'm going to inject some voltage here and then go under the thermal camera, so I can confirm if the APU RTC section is faulty or the EC before. Besides, the AMD Kabini CPU, all AMD CPUs don't need 3.3 volts for the RTC section. It needs 1.5 volts. It's called VDDBT RTC_G. The RTC VDDB G means for the mechanical off. G state. G3 is the mechanical off state. Only the RTC battery is present, not the battery, the main battery or the adapter is plugged in. So before the adapter is plugged in or the main battery, it is called mechanical off, which is the G3 state. That is why it's called VDDBT underscore RTC underscore RTC underscore VDDB underscore G, which is the name, standard name for all AMD's APUs, Ryzen's, Cabinis, Bristol Ridge, all of them uses that name, which is a standard name given to it by AMD, right? And that uses 1.5 volts. So I don't need to inject 3.3 volts to find it. But for demonstration purposes, I can show you that the EC most likely is broken. So the EC standby name, let me go back over to the microscope. So the EC standby name is AVCC. Right, so AVCC, as you can see, this is the EC, it's a KB9022QD, right? As you can see, the D indicates that it is a embedded firmware that is inside, so it doesn't need to go out and read an EEPROM chip to configure the GPIO pins, yeah? So pin number 67 for the E&E. Remember, I'm working from experience, right? So this is pin number 1, mark. This is pin number 1. Here's the mark, right? So this is 32, right? And 32, and this is 64, right? As you can see, 65, right? 66, 67. I get a dead short there. As you can see, I have 2 coils here. One is connected to ground, and one is connected to the linear. This coil indicates that it's going to be grounding the internal SPI ROM inside of this embedded controller. So this is going to carry an analog ground to provide ground for the internal EEPROM chip that's inside, right? This coil is providing L10 is providing 3.3 volts to the AVCC pin of pin number 67 to the EC, right? So the EC, this is the standby name. The next one is pin number 37, which is the reset signal. As you can see, we have, this is 32, right? Pin number 37, 33, 34, 35, 36, 37, and that's okay. As you can see, this is another coil here, right? And this is pin number 37, 33, 34, 35, 36, 37. This is the reset signal, and that's okay. But I have a definite short here on the AVCC line, which is pin 67. So as you can see, the EC is broken, right? So I'm going to remove the EC, and I'll have to program a new EC on it, and hopefully I should get some lights and power on, right? So I'm going to replace the EC now. Right, so let's do this. All right, so I'm now setting my hot air to 400 degrees, and I'm going to use the tweezer here, and I will remove it. Where is the other one? Oh, here it is. Let's do this. What I'll do, I'll just tin it with some. Yeah. Alright, so I'm just waiting for the iron to get hot. It doesn't matter if there's bridge because I'm removing. Alright, so I'm just gonna remove it now. And it's removed. So I'm just gonna tin in the leads to solder the new chip. Oops. Alrighty. Okay. It's all good there. Alright, so I'll just clean this now. So I'm going to check the resistance now, and then I'm plugging the power and to see if the chip will get hot. Still get hot. Then I can say that the diagnosis was correct. Then I'll Alright, it's now clean. All the pads are tinned with solder and they are looking nice and shiny, as you can see, and they are all ready for soldering the new embedded controller. Alright, so now I'm going to check on the capacitor for the pin number 15, 3.3 volts. Alright, here it is. So let's come in some more and see what we get. So I'm going to measure on the pad on the JP1 and take a look at the meter. Oh, the meter shut off. Alright, so take a look at the meter here to see the resistance, to see if my diagnosis was correct. Now I get 642, 44, 45. So my diagnosis was right. Right? So if I go back up to the embed controller standby pin AVCC and that coil L10, I get 646. So the short is gone. So it was the embedded controller. So I will get a new one and program it using the SVOD ZIF socket, which is a very handy socket. Saves a lot of time before normally we have to use the keyboard connector and to use the adapter, it is a very troublesome way to get it to connect, and sometimes it doesn't work. It says verification always falls or whatever. So the zip socket is what we're going to use. So I'm going to get the chip and then I'm going to install. Okay, so I have found them. I have some new ones here in that package, as you can see. So I'm going to take one and program. As you can see, the number there, if you can see, it's a, take out one of them. It's a KB9022QD. Alright, so it's a KB9022QD. So I'm going to take it out. This is a brand new one, as you can see. So I'm going to program it. Using the SVOD socket, ZIF socket. Alright, so I'm going to get the ZIF socket now. Alright, so this is the ZIF socket. I think I'm seeing a bent pin here. Oh, it's not bent. Oh, I thought the pin was bent. Okay, so I'm going to insert it. As you know, it all goes in one way. This is a very good tool. Saves a lot of time. Alright, so let's remove this out of the way. Alright, so it's locked in place, as you can see. Sorry. Alright, so I'm now plugging in the adapter. I don't think I have this installed. Let me set up the programmer now so I can program this embedded controller. All right. Okay, so I have set up the programmer. So I will now head over to the programmer here, as you can see. So I'm going to select ENE, and I'm going to select, first I'll have to download the ZIF socket. because I haven't have this on my lap. This is a new machine I've been using. So the ZIF A&E should be this one, download pinouts, and it says yes. Alright, so I should now select motherboard. Oh, I already have it here. Beautiful. So I select it. Motherboard must be unplugged. There we go. There we go. So I click read. Now I can access. As you can see, it says E&E, right? ZIF E&E, and it's KB9020 KBC, and it is true, and everything is okay. Voltage set to 3.3 volts, and erase, blank check, verify is also checked. So I will now download I have the BIOS already. Sorry, I don't think I need to log in. I'll log in anyway. Alright, so I'll go to open. Let me see if I can search for it here first. So it's LA-C781. Yes, this is it. Let me see if I can. So it says E&E U44 KB C7081. I drag it in and I click write. So as you can see, it's now writing to the embedded controller. Quick and fast, very easy, effortlessly, no hassle, no pain. Right, by using the keyboard connector, that method is a mess, right, and it doesn't work properly. But using the ZIF socket here, you can program an EC before soldering it to the board, so you know that the EC is programmed perfectly without have to be worrying if it's going to work when you're soldering it after soldering it on the motherboard. Then you have problems to be able to, oops, see, we say verify false. So I'll have to check the pins to see if all the pins are connected to the board properly. So let me pause. Alright, so I'm going to try again. Alright. Alright, there we go. Alright, so I'm going to select A&E. Alright, select the motherboard. Okay. Alright, so I'll see I have a connection issue here. Let me recheck again. Okay, so it was connected, so I'll now read ID. Select mode of programmer. Oh, sorry. And select the ZIF socket again. Alright, there we go, there we go. Read, and then I'll write. Alright, let's see. Alright, so I think this should pass. Perfect. So the job is done. So I can now solder this to the board. Alright, so I remove it, unplug, don't need the program anymore. And my regular SPI socket, 200mm socket, and I will now remove the EC. There we go. Alright. Alright, back under the microscope. Hold on, let me check if I... Alright, just sending a text message there. Sorry about that. Alright, so I'm going to solder this part. I think I'm going to pause the video because of time. So I will skip this part and then resume when I'm finished soldering this strip. Okay, so I've soldered it, as you can see there. Just going over the legs, making sure that they're all perfectly soldered. Alright, so I will clean it now with some 99.9. Let's see if I get lights at the DC jack. We call it the light of life for HPs. Alright, so I'm just drying it. And at the same time I'm inspecting the legs if there's any bridge, solder touching other legs. I'm actually drying it. Alright, so I'm just inspecting it now for any bridges to see if there's any legs that are touching. Alright, all this side is all good, no bridge. And this side, yeah, and I don't see any bridge on this side and on this side. I think I'm all good. Alright, so I'm gonna measure the resistance again on the pad there. Oh, let me... Okay, so I was getting my camera back. Alright, so I'm checking on the pad there, PJ1. Oops. Alright, so checking it now. I get 473 there on the linear power supply, and that's good. And on the coil here, this PL10. I get 474. So let's see if we get some white lights now. So I'm going to plug in the charger to see if we get the white light glow at the... Alright, checking to see if I'm getting white lights. Is this the one giving the white light? Let me try the other port. Let me try the one in the board. Still not getting a white light. Okay, so I'm not getting a white light, so I'm just going to inspect under the microscope to see if there's any bridge, because maybe I overlooked. So let's go back under the microscope and see if we're having a bridge. So I'm thoroughly looking here. Alright, not seeing anything. Alright, let's check this side. Okay, I see a bridge. I see the bridge right there. You see it? Right there, there's a bridge. Let me see if I see any more. Alright, let's check the next side. Alright, so I think that's the only spot there. I see a bridge right there. One small bridge. I overlooked that one. And it's right here. Alright, so I'm just waiting for the iron to get hot, and then I will clear it. It's not hot enough as yet. Alright, there we go. Alright, so it's cleared. Alright. Alright, so it's now gone. No bridge. Alright, no bridge. Alright, so I'm gonna try again. Plug in the power. Still not getting a light. Let me try this. So I think one of these doesn't give light. Let me see. Let me try about the case again. Still no lights. Okay, so I realized that the program that I flashed inside of the EEPROM inside of this KB9022 QD was not correct. So I wasn't getting the lights, so I had to pause the video because of time. Unsoldered the chip, find a different firmware from the HP website, and then I dissect it and created the file, the bin file, and program it. So now I get lights. See, I'm plugging in. See, I get the light now. So as you can clearly see that. So the firmware that I had. I don't remember where I got it. I had it years ago, but it doesn't work. Can't recall because I rarely program these chips because they don't really go bad. All the time they go bad is when they got hit by static electricity or some over voltage, or from the battery side, or by plugging in a wrong adapter can burn these embedded controller. Alright, so I am going to connect the power again. Alright, so a closer look. So there's the light. I have a short in one of these wires, so I'm going to give power. See if I can trigger the board. Alright, so here's the switch. Yes, as you can see, the current is now 400 milliamp. I have to stop the power because I don't have the heatsink on the APU. So I'm just going to connect the APU heatsink. Alright, so let me zoom out. I'm just going to connect it in the board, in the case. I'm just going to connect everything in the case. Alright, the heatsink. Heatsink 1. Alright, so I'm going to plug in. Alright, so I'm going to pause. Okay, so I just put a screw that the board don't fall out because, as I said before, I got it as is. Alright, so alright, so I'm going to connect the power now. And see. What do I get? Alright, light is there. Alright, so I press the switch. There we go. We have peak display. Oh, I didn't connect the fan. Alright, so it's now booting up the operating system. Let me move this out of the way for you. Oh, it has my name on it, as you can see. So the person has my name. Interesting. Alright, so it's all good. Okay, so we're in the desktop now. You can see there. Alright, so I hope you enjoyed the video. Alright, so I had a bad file there and it didn't work. So I had to get one from the HP website, decrypt it, regular synthesis of the BIOS using WinHex, and I created this one, which is from HP official's website, and it actually worked. So I hope you enjoyed the video, and I hope you like and subscribe, and I will repair something again for you in my live stream on Saturday. Alright, so see you again on Saturday. Bye.